Okay. Great. So we do speak in English today. Of course, questions as regular you can then ask in Hebrew. Don't really care. What we will do is we will finalize our treatment of Bose-Einstein condensation. And then we will turn to the last chapter of this class, of this course, is again phase transitions, but from more modern. Called resonance. And then we will continue to modern description of phase transitions, and we will see till where we go. Now, practically, we have this set of lectures today. We have next week. The last lecture is on Monday, February the 3rd. It's a problem because the exam is on February the 6th. So what I propose is to cancel the last lecture. It's just 1 hour. And I will provide another lesson where I will solve old exams or stuff like that. And we won't learn new material basically at the last week of the semester. Last week is the February the 3rd, not next week. Anyhow, so let's see where we've stopped yesterday and what we already have in hand. So first of all,
okay. Shit.
Yes. It stopped sharing. You are sharing. I'm sharing.
אנחנו רואים את הזום.
כאילו צריך לעשות הקטנה בצד של ה...
You want to find. Okay. Let's do this downwards.
זה החץ הקטן למטה.
Well, this guy?
Yeah.
Okay. And I will shift it somewhere. Okay. I have limited space. I tried to find a normal classroom, but everything was occupied during those hours or between 9 and 12. Sorry about that. So we're dealing with Bose-Einstein condensation. What we managed to obtain is the following solution. The average number of particles in the system is equal to G0, which is simply the degeneracy that we have, multiplied by the volume, divided by lambda t to the power 3, multiplied by this polylogarithmic function of zeta, when zeta is simply e to the power beta mu, okay? And lambda t was a square root of 2 pi h bar squared divided by m k Boltzmann t. So those are the results. And then we started to describe what actually happens, why it happens, and et cetera, et cetera. Now, those results, as I tried to tell you, are in some sense a little bit absurd. Why? Because we assume that we can control the average number of particles inside the system. We assume that this n over here, this n over here, is basically something that we can control. We replace the average value by the total number of particles that we assume that there is in the system. Okay? So we replace this as we did for fermions. If beforehand it was mu and were the parameters of the system that were controlled by us. Okay, this is how we applied the generalized grand canonical ensemble. What we actually want to control is the number of particles and temperature. Okay, so instead of doing this, what we are doing is we're controlling the number of particles. Oh my God. The number of particles and n. So let's wait for a second. Somehow my Apple Pencil lost all its battery, all its juice. I'll wave my hands a little bit. And the idea is it's a mathematical mapping in some sense. The idea is that constant n, specific n, it's hard to solve, and it's hard to take into account all its possibilities. Why? Because the moment I constrain over something, basically limits the overall possibilities, okay? And the calculations, the technical part of the calculations become difficult. What we do is we lose this constraint. We allow for n to be whatever you like, to perform the calculation, and then we say at the end, just at the end, let's do the switch. Let's say the average number of particles is the controllable parameter, the temperature is the controllable parameter, and what is left, what was controllable parameter when we started the calculation, this mu over here, okay? This mu over here, instead, we now say, let's look on two other parameters, which is n, the total number of particles, and the temperature, okay? Why? Because think about it from experimental perspective. I can control the number of particles inside the system. I can put my system inside a box, and I put some external fields and specific boundary conditions and external walls, etc., etc. And eventually the number of particles is set, okay? But so I can control it somehow. It's really hard to control chemical potential. It's something about the intrinsic properties of the system. It's hard to control. Temperature I can control. I know how to control. And the number of particles I can say, well, let's close it and we'll assume that this guy is constant. Now, when we look on this from this perspective, when we look on the behavior of the system from the perspective on n and t, we have a problem. Why we have a problem? Well, we have a problem because this n now multiplied by lambda t to the third divided by v and divided by g0, okay, which is just generosity, it equals to this guy f3/2 the fugacity, okay? Now, n I can control, and I can set it to almost whatever I want. V I can control. G0 over here is simply degeneracy. It depends on my particles. So usually, if I want to look on this from the perspective of quantum numbers, so G0, it's simply the 2s plus 1, okay? So if I have the total spin of 1, so I can have a spin of 1, 0, and minus 1. So this is the degeneracy. And lambda t, we see what lambda t is. Lambda t is this guy, okay? So it's basically, so it is a temperature, okay? I can set my temperature to whatever quantity that I want. So the left-hand side of this equation is a number that I can make big or large. I control the number. On the right-hand side, I have a formula that in general depends on what? It depends on this psi over here. So it's basically depends on the temperature inside my system and mu. Now remember, there is a big problem with mu. Mu is less than 0. Otherwise, all my machinery, all my mathematical calculations will fail, okay? And this is the same, some similar problem we had for fermions. You apply a machinery, you apply a function, but you had limitations in between, okay? You had some sort of constraints on the values of mu, right? You cannot just say, well, let's forget about those and do whatever we want. No, you have to take into account those limitations. And mu was limited, okay? Specifically, it says the following thing. If we plot this function, this polylogarithm function, f3/2 zeta, as a function of zeta, we know that it rises up, starts from 0, rises up, approximately exactly up to the point when zeta equals 1, okay? And it gets the value of 2.612. And that's it. It doesn't go above that. So this means no matter what our temperature, no matter what's the number of particles we have, no matter what's the volume, etc., is n divided by v multiplied lambda t third power g0 is always smaller than 2.612, etc. And this is the problem. I have almost any number on the left-hand side of the equation, and it's limited by this number of 2.612. Okay, so the question, why mu has to be smaller than 0? Because we assume that our lowest energy starts from 0. Our energetic spectrum of free particles inside the box started from 0 and rised up. Okay. How we explained it? What happened wrong? So we assumed several things. One of the things that we assumed, maybe the discrete spectrum of the problem is not exactly discrete. And we found out that, well, it is discrete, but the difference between the levels is extremely narrow. It's on the order of 10 to the minus 14 Kelvin, okay? And it's measured in Kelvin as a temperature. So extremely dense energetic spectrum. The other problem that we discovered, that's what's the real problem, is what happens to the occupation numbers, okay? So if you remember, the occupation number of level epsilon equals to 1 over e to the power beta epsilon minus mu minus 1. Okay. Now, if we look on the lowest, possible epsilon, which is going to be 0 from our perspective. If we look on the lowest possible level, so as we lower the temperature, okay, look on this guy. Okay. What happens? So we keep n constant, we keep v constant, g0 is constant, okay? And we lower the temperature. See, the temperature enters here as 1 over square root of t. So what happens that here stands 1 over t to the power 3/2, okay? So this guy goes as 1 over t to 3/2, okay? So I'm lowering my temperature and I'm lowering my temperature, okay? What happens as I lower my temperature, okay? Oh, I'm sorry. So what happens as I lower my temperature is that 0, or this fugacity, gets closer and closer to 1. So basically mu approaches 0, or mu approaches the lowest possible energetic level, okay? So what happens when mu will start to approach the lowest possible epsilon that I will have? I will get a 0 over here, okay? And e to the power 0 minus it's 1, and 1 minus 1, it's something that can explode. This is from one hand side. But on the other hand side, the total number of particles is smaller than n, right? So if you look on this always smaller than the total number of particles, okay? So our idea was the following. What actually happens is that the lowest energetic level, if we look on all the possible energies that we have inside, so we'll start from 0 and we go up, okay? Mu, which is some sort of energy, right? Like Fermi level. Mu is somewhere over here, okay? So we have mu over here. As we decrease the temperature, U goes to start to approach to 0. That's what we see. The fugacity goes to 1, okay? Now, it cannot reach 0 exactly, okay? Because otherwise, this guy will explode, and it's limited by n. So what will happen? What will happen is that as mu approaches closer and closer and closer to 0, which is our lowest energetic level, at some point, all the particles have to sit exactly at the lowest level. You can say, well, yes, some of the particles are going to sit at the lowest level, and a little bit more particles are going to sit on the some additional level, yeah, like epsilon over here, and another particles are going to be sitting at epsilon 2, and et cetera, et cetera. So we'll have a spread, everything's fine. But no, this explosion, it actually protects the next levels. Okay, so this guy will grow up until almost it reaches all the end. It means that almost nothing, not almost, but not a lot of particles are actually somewhere in those excited levels. And this is called condensation. Condensation is when a proportion, macroscopical proportion, it's important, it's not 3 particles or 7 or 8. It's a macroscopical proportion of the total number of particles that we have inside a system are sitting exactly at the lowest level. Okay? Now, think about it. We have one level. We have a continuous spectrum, one specific epsilon, where the function is huge. Okay? If I plot it, this is an epsilon as a function of epsilon. So I will have some sort of a continuous distribution or whatever. But what happens at 0, exactly at 0, I have a delta function. And I cannot neglect this delta function. And in all our integration that we've done, we assume that the function that we all integrate over is continuous function. Nothing happens, right? We neglected this guy. And we couldn't, because it's not protected by any other levels from U to approach this minimal epsilon. Yes?
If mu approach epsilon?
Yes.
Okay.
Yep. Other questions? Okay. So that's what we showed Tuesday. How we mathematically describe what happens over here, right? So if I want to look on the, for example, if I want to see what happens, if I want to see what happens as a function of temperature on the 0 level, the average number of particles at the 0 level, divided by the total number of particles, okay? So what happens to this quantity? So I know that somewhere when the temperature, whether this temperature goes to 0, okay, this guy has to be 1, okay? That's I know. Okay. Now, what happens at large enough temperatures?
0.
It has to be exactly 0 because n is very large, okay? And it's a continuum spectrum, so the number of particles, they just do not attract to a one specific level, okay? So at large temperatures, I will have exactly behavior that it's exactly 0, not approaches 0, it's 0. Why? Because n here is on the order of the Avogadro number. It's 10 to the power 22, okay? So we have huge number of particles, and somehow we have continuous spectrum, and all of those particles somehow reach over here. Now, what kind of transition would take me from here to here, okay? And that's the question, okay? What happens? So what we expect to happen okay, and I will explain you in a second, that there exists a critical temperature, let's call it Tc, okay? And at this Tc, so below this Tc, the number of particles at the, or the ratio of particles that are sitting at the lowest level is exactly 0. At Tc, this guy will start to rise somehow and will eventually reach this number 1, okay? And what happens over here, this is what we called Bose-Einstein condensate. We have number of particles which is proportional to the total huge number of particles in the system that sit in a 1 microscopic level. Now, the applications of this thing are in quantum mechanics are enormous, because if they're sitting exactly at the same level, they can be described by one single wave function, and then something very interesting happens when one single wave function describes huge number of particles, okay? So if you know what superconductivity is, or if you know what superfluidity is they are occurring when everything is described by this Bose-Einstein condensate, okay? Great. So if you want to see the intuitive picture, what is the huge difference between fermions and bosons, okay? So for fermions, we have bosons. So what we've seen for fermions is that whenever we have an energetic spectrum, this is our epsilon, we know that all the fermions, they sit one on top of each other. Huge number of fermions. At some point, the interactions are not important, and they occupy all the energetic spectrum up to some specific mu Fermi. So all the effect, it's a cumulative effect of a lot of particles, okay? Because the only thing that matters, what happens at Fermi level. The Fermi level is extremely high. Everybody contribute. All the energies are important, okay? For bosons, it's the other way around, okay? So if we look on our energetic spectrum, what happens that all the bosons are sitting at the lowest energetic level over here. They mostly occupy one single energy. So if here all the energetic levels are contributing somehow, and the total effect is the effect of all the energies, for Bose-Einstein condensate is just one specific energy that matters. Okay, so if you think about it, there is always one big guy that actually acts and describes everything for bosons, for condensate state. As for fermions, it's something very, very different. It's a cumulative effect. All the energies are important. Just the energy equals 0 for bosons, all the energies for fermions. Okay, now, how this looks. Okay, so we have a prediction. I said, well, it should go something like that, but why not, a straight line? Or maybe something like this. Okay. Why does it have to behave in this fashion? So for this, we can actually predict something. Now, moreover, what people see in experiments, right? So what I described to you, it's a microscopical description. What happens at the lowest level? But who can actually go and measure what happens at the lowest level for particles in a box? I see a lot of particles, right? I can heat them up. I can they're quantum particles also. I even cannot basically follow them. So how can I know how many particles are at the lowest level, and et cetera, et cetera, et cetera? So this is not something that people go and measure, okay? People go and measure heat capacity. People go and measure the reaction to external force and stuff like that. They do not measure occupation number. So if we want to see where it occurred, so nobody went and measured and looked on the occupation number of the lowest level. People measured something else, specifically heat capacity, and then they understood whatever happens backwards. Okay, and we'll try to see how exactly this peculiar behavior occurs on the level of heat capacity. Okay, so if you want to remember something about the Bose-Einstein condensate and its connection to fermions, is this specific picture. Contributions of the many for the fermions, condensation on specific level, and contribution from a single specific level, which is most important. Okay, so what kind of math do we have inside? So I remind you, what kind of formulas do we have? So we have the following formula. First of all, we know that the average number of particles, n, equals to G0V divided by lambda t to the third power, F3 halves of fugacity. Now, instead of just saying, well, those are the total number of particles, we can say, no, those are excited guys, because we know that something else happens at the lowest level. So those are the number of particles at excited states. Okay. What happens to other particles? Okay, well, the total number of particles is n0 plus what? Plus n excited. Okay. It has to be like that because, well, this guy was computed based on the regular behavior. We know that something peculiar happens at the lowest level. So let's just add this delta function behavior at the lowest level. So we just add this n0. Okay. Now, what is n0? N0, it is 1 over e to the power beta. And we have 0 over here because the lowest energy, we assume it's 0, minus mu minus 1. So it is 1 over the fugacity to the power of minus mu minus 1. We just write it down as the fugacity divided by 1 minus the fugacity. Okay, so in total, n, it is fugacity divided by 1 minus the fugacity plus G0V divided by lambda t to the third, F3 halves the fugacity. This is the total number of particles, at least at the lowest, below this TC, below this temperature where the number of particles at the lowest level become important. So first question to ask, okay? First question to ask is, what is this TC, right? What is this TC? So we know, so what is the critical temperature? Critical temperature below which the condensate appeared. Yes.
אמרנו שעבור טמפרטורות גבוהות, המצב אפס לא מאוכלס.
כן.
נכון? אז איך זה, אז עבור טמפרטורות גבוהות, מה פותר את הבעיה שלנו מקודם? המספר הממוצע של החלקיקים הוא מוגבל מתחת לאיזה ערך?
Okay, so I will rephrase the answer or the question. So what we see is that the number of particles at the ground state for large temperatures, high temperatures, is almost 0. Okay, Now, why it happens? So it doesn't mean that n0 is exactly 0. It's not 0. It's something. This something is small. And we take something not large, and you divide it by a huge number, we can say it's 0. Okay? So it's limited to something on the order of 10 to the minus 22. Okay, so it's extremely small number. It's not 0. It's on the order of 10 to the minus 22. Okay, this ratio is on the order of 10 to the minus 22. It's extremely small. You don't care about it. As you cross this TC, n0 becomes not minor quantity. It becomes something on the order of n. So it becomes on the order of 10 to the 22, and you cannot neglect it. So when I'm going back to this expression over here, this applies for t below TC. For t above TC, I should only care about this guy over here. Okay? Fine. So the two contributions come only at the condensate regime. You above the condensate regime, where is no condensate, you care about the excited states. Think about it. When everything is continuous, you can always take one energetic level and kick it out. You don't care, because you have a huge number of particles. Well, there are going to be 10 particles at this state, so you don't care about 10. You have 10 to the power 22. That's it, right? Any other questions? Great. So how we observe this guy? So we say the following. We know that G0 V divided by what's this guy? Sorry, it's the other way around. Right? So we had this expression. There it is, where we started. This guy. That's what we had. Okay? So we know that n divided by v lambda t to the third G0 equals or less than 2.612. Okay? Now, if we substitute everything, so we substitute, just so before substitution, if we say, what happens at exactly the critical behavior? So at some point, this fails, right? This guy fails to describe at some specific critical temperature, okay? This inequality fails. When it exactly fails, when the inequality becomes equality, and below any such temperatures, the mu cannot grow, and something else happens, all right? And then everything fails, but exactly when this guy equals to that guy, this is my critical temperature, okay? At criticality, or just above criticality, for temperatures larger than TC, okay, the inequality works, because I haven't done anything wrong. At criticality, it reaches its limiting behavior. So mu goes to a specific point above which it cannot grow at all. So when it happens when n, v, lambda, let's call it TC, the third power, divided by G0, smaller or less than 2.612. Okay, so we can take out of this guy the TC, and we will get, okay, that TC equals to 3 Kelvin. So what I substitute the mass of helium-4, and I substitute volume is 1 liter, and I substitute n 10 to the power 22. Okay, so I have Avogadro number of particles of helium-4. I substituted all my expressions for lambda TC, for everything. inside here, and I get a critical temperature. Yes?
What's G0 for helium-4?
G0 is going to be 3.
What's the spin of helium-4?
I think it's 1.
Okay.
Okay, now if I'm going and measuring critical temperature, and I will say exactly what I measure and what I look. So in a lab, I'm going to measure TC of 1.17 Kelvin. So extremely close, okay? Extremely close. I haven't told you what exactly I measured, but I'm saying, well, the appearance of a Bose-Einstein condensate in a lab for helium-4, it's appearing on the level of 2 point something Kelvin. It's extremely low temperature, okay? If you want to, it's not 0, okay? It's a minus 270 something, okay? Celsius, 2.17 Kelvin, and something appears over there, okay? So let's describe what exactly appears and how this behaves. Okay, so I do know that if I'm plotting the spectrum, not spectrum, the occupation number divided by n, I have T, and I have N0 average divided by the total number of particles. We'll have here TC, and this TC is approximately 3 Kelvin, and I have a 0 above it, and I have something over here that will try to explain what exactly happens over here. Okay. Great. How do I find it? So first of all, let's go and calculate what is the total number of excited particles. So unexcited average, we know that is G0V lambda T to the 3rd power. And here we have F3, and usually there a fugacity stands over here, right? So this is a fugacity. But if we're looking for T below TC, we know that the fugacity cannot be larger than 1, okay? So the total number of particles, excited particles, we still count all the levels except the ground state, okay? So this computation is correct for every particles that are sitting on where? That are sitting on all the excited states. This can be whatever I like, this part. This also, lambda T, depends on the temperature. I can control the temperature. And the only thing that's uncontrollable when it's getting stuck is the fugacity. So for T below T0, the fugacity has to be equals to exactly 1. Okay, that's what happens. So I know that NE average equals to G0V lambda T to the 3rd power, F3 fugacity, not fugacity, but 1 over here.
Can I ask a question?
Yes.
Earlier you wrote an expression for the total number of particles in the mechane, 1 fugacity.
Yes.
How could it be? The fugacity equal to 1.
But, okay, so if I'm, so the fugacity, great question. So this is some sort of a approximation, right? So the fugacity is e to the power e to the power beta mu. Okay? So if I'll stack 1 over there, as you pointed out, so if I'll have fugacity divided by 1 minus fugacity, okay, the fugacity will explode and everything collapses, right? But I know that this guy, so the fugacity is not exact, then the fugacity is not exactly 1 because this guy have to be smaller than n. Okay, so the fugacity is not exactly 1, but it's getting there.
Okay.
It's getting there. Now, so for this guy, it's limited. You're right. but this function approaches this number. It's not f of 3, it's f of 3 divided by 2. F of 3 halves, f of 3 halves. Okay, so I know when fugacity approaches 1, this guy approaches the total number of particles. Okay, but f of 3 halves of fugacity approaches a specific number, which is 2.612, which I will just write down of f3 halves 1. Okay, so here it's a big number. Here it's a finite number, which is close to 2.612. It's maybe not exactly 2.612, but it's extremely close to it. Okay. Okay, so this is n-excited. Now, what is the total number of particles that I have inside my system? What is the total number of particles? I know that the total number of particles that I have inside of my system are spread out everywhere for the critical temperature. Okay? So exactly the critical temperature, N equals to N excited. Okay? What is T equals to TC? Because I don't care up to the critical temperature. I don't care about the number of particles that are sitting at the ground state. I don't care about them. Okay? So exactly at critical temperature, the total number of particles is G0 V lambda, and we call it TC to the third power. And here we have F3 halves one. Why again? It's one, well, this is the point when fugacity approaches to, or the chemical potential approaches to the lowest level, and this function over here, which is the function of fugacity, approaches to this number 2.612. That we, instead of writing 2.612, we write F3 halves of 1. Okay. So the quantity that we are interested is N0 average divided by the total number of particles. Okay. Now let me write it down, not with this fugacities, because as Oz pointed out, fugacity is not 1. I cannot use this long expression. I don't know exactly what fugacity is, okay? But I know, so it's hard to use this formula over here. It's hard to use it. In some sense, it's useless because I don't know exactly what is my fugacity. But I know the following thing. I know that I write down the denominator in the following term. It is simply N minus N excited divided by the total number of particles. Okay. So this guy equals to, this all for T below TC. So this guy equals to N divided by N minus N excited divided by N. N by divided by N simply 1 minus the excited, we know what's excited is this guy. The total number of particles is this guy. Okay, so if we write down everything, we will have G0 V lambda T to the third power F3 halves of 1 divided by G0 V lambda TC F3 halves of 1. Okay, and you see that G0 V F3 half of 1, F3 halves of 1, everything cancels out. So eventually we obtain that N0 average divided by N for T less than TC equals to 1 minus lambda TC to the third power, divided by lambda T to the third power. Now, let me remind you, what is lambda TC or lambda T in general? I never remember this guy. So lambda T equals to a square root of 2 pi h bar squared divided by m k Boltzmann T. Okay? We substitute this guy inside and we obtain that n0 divided by n equals to 1 minus T divided by Tc to the power of 3/2. Okay? So if we look on this, n0 divided by n, this is our temperature. We have 0 for any temperature that is equals to Tc, and we have this guy for any temperature that T is lower than Tc. So this is the expectation, but this expectation cannot be verified experimentally. Okay? We cannot see this. We cannot go and measure, at least not back at those times. Okay? What we can measure, but this is a classical example of condensation, right? And we have an explicit mathematical form to describe it. But what is measured, it's not this condensation picture, it's something else. What is measured is the behavior, it's the behavior of the specific heat. And what we are going to calculate is the behavior of the specific heat. How CV is behaving above Tc and below Tc. So this is the next question. We understand now the physics. We know that there should be condensate. We just want to see how experimentalists will observe this condensate state. Okay, and in order to do this, if you remember, CV equals to du to dt with constant volume. So we need to find u. Okay. What is this u and how it behaves? So first of all, in order to find mu, okay, u is somehow related to this grand canonical potential. If you remember, u was equal psi equals to u minus Ts minus mu n. Okay. Now psi we know. We found it in the previous lecture, and psi was equals to minus 2/3 G0V divided by 2 pi squared 2m divided by h bar squared 3/2, and we had this nasty integral from 0 to infinity epsilon to the power 3/2 divided by e to the beta mu minus epsilon minus 1 d epsilon. Okay. So what we need to do is to calculate this nasty integral. I'm not going to do it again because I already shown you how to calculate integrals of this kind. So we have seen how to calculate an integral from 0 to infinity of epsilon to 1/2 e to the power beta epsilon minus mu minus 1 d epsilon. Done that. Okay, remember, expand everything, use the Feynman trick, do a substitution, sum everything up, and voila, you get this polylogarithmic function. Okay, so if you do this for the energy or for the psi, you'll get the following result. We obtain that psi equals to, let me see, minus G 0 K Boltzmann T V divided by lambda T to the third power. And here you're going to have this polylogarithmic function F5 halves of the fugacity. If you really want to observe why, just perform this calculation, but it's similar. It's exactly the same thing as what we did on Tuesday. Okay? Now, again, you see, this is done for T larger than TC. Okay? Because how we obtain it, we have to perform this integral, and there is some sort of a Bose distribution inside. And again, we neglect the lowest level. Okay? So for T below TC, there should be some additional contribution. Okay? Some additional contribution. What is this additional contribution? Well, we will have psi equals to the contribution, lowest level contribution, minus G0 K Boltzmann T V divided by lambda T to the third power F5 halves of Z. Okay. Now, what is this lowest level contribution? How do we find it? We know that N0 average equals to the fugacity divided by 1 minus the fugacity. Okay. Now, the grand canonical potential is the sum over all the grand canonical potentials of all the different levels. Okay. So if we call all of this as psi 0, okay, and in total we have psi equals to psi 0 minus G0 K Boltzmann T V divided by lambda T to the third F5 halves epsilon. We know how to relate psi 0 and N0 average. Okay. We just look on the ground state and we say, well, we need to calculate the contribution to the grand canonical potential that comes from this ground state. Now, the grand canonical potential determines the average number of particles at this state. How it relates? We know that N0 average equals to minus D to D mu, okay, of psi 0. Okay, this is on one hand side. On the other hand side, we calculated, and we know that it equals to e to the power beta mu divided by 1 minus e to the power beta mu. Okay. So out of this guy, and the connection to this guy, you can find psi 0, okay? So we have psi 0 minus d to d mu equals to e to the power beta mu divided by 1 minus e to the power beta mu. We solve this equation. You just need to perform one integration with respect to mu, and you obtain that psi 0 equals to 1 over beta log of 1 minus e to the power beta mu.
How do you determine the constant?
Which constant?
Do you have any integration?
So you want a plus c over here.
Yes.
Okay. Does it matter? Does it matter if I add to the grand canonical potential a constant value? Does it matter? So remember, what is this psi?
It's just the...
It's the thermodynamical potential.
Yes.
If I'm talking about energy, does it matter if I add to energy a constant?
This constant can depend on the temperature. Yes, it does not depend on mu.
Okay.
Maybe it has a beta dependency, and now it's matters.
But I said the constant have to be 0, or when I find it out, okay, so you're saying that it's some sort of a CT.
Maybe.
Maybe. Okay, so let's leave it like without this C, and I will explain you maybe later why this C can be 0. Okay, it's a good point. Good point. Anyhow, psi now equals to 1 beta log of 1 minus the fugacity minus G0 K Boltzmann T V divided by lambda T to the 3rd power F5 halves the fugacity. Okay, now one last thing to add over here, the degeneracy, this G0 over here, it's not only present on the excited states. It has to be present also for the ground state. So we have to add this G0 over here. Okay, why? Because if the degeneracy is for all the excited states, it's also present for the lowest state. That's it. Okay. Now, we have this, and then we can use the connection between the psi and u. So again, if psi equals to u minus ts minus mu n, okay, so this is the ground canonical potential. What is the connection between psi and u? So I know psi. How do I find my u exactly? Okay, so what is the connection between psi and u? So u equals to some derivative with respect to something. Okay. So what I have to take derivative can show, or we showed it previously, for any potential, you have to take the appropriate derivative. And for the ground canonical potential, you have to take the derivative with respect to beta of beta psi when you keep beta mu constant. Okay. So all those are all the different Legendre relations. If you have one quantity and you perform a Legendre transformation, you have another quantity. How you go backwards, you have to take a derivative with respect to some specific parameters. And those are the parameters that we have for you. Okay, great. So now we can take this guy. We take a derivative, we obtain u. We take another derivative, and we obtain CV, du to dt. Okay. The problem is the same problem that I think Oz pointed out before for the calculation for the total number of particles. And I don't know exactly how fugacity behaves below the critical temperature. Okay. The whole problem with this approach is how fugacity behaves for T lower than Tc. Okay, so I cannot simply say, well, the fugacity is 1. If I will substitute 1 over here, the logarithm will explode, and nothing good happens when functions exploding. So we overcame this issue for n0 when we said, let's look only on the excited part. Okay, let's look only on the excited part of the system. The same is going to happen over here. I'm going to try and look only on the excited part of the system. Okay, only on the excited part of the system. Okay. So the only thing that matters to me is this part, guy. So when I take a derivative, so if I take d to d beta of beta multiplied by minus G0 K Boltzmann. So let's erase it and we'll say 1 over beta d lambda t to the 3rd multiplied by f to the 5 halves of e to the beta mu, okay? And I take the derivative while keeping beta mu constant, okay? What I will obtain, and will save to you the exact derivation, it is that u, this is u, is equals to exactly 3/2 k Boltzmann t, g0v lambda t to the third power, f 5/2 of the fugacity. Okay. So basically the only thing that I have to take the derivative of is this lambda t. And lambda t we know it's 1 over k Boltzmann t to the power of 3/2. This is where the 3/2 are coming from. Okay. So this is my potential, my energy. Okay. The energy of the lowest level is not important. Well, because we don't know exactly what fugacity is. Okay. And also, look what I have. So if I multiply this part by beta, beta cancels out, and then I take the derivative of this part, okay? Let's see. What happens if I'll take into account the ground state? So I have d to d beta of beta multiplied by g0 divided by beta log of 1 minus e to the power beta mu, okay? And I have to take this derivative when beta mu is constant. Beta and beta cancels out. I don't have a direct, so the only thing that depends on beta is beta mu, but beta mu is kept constant all the time. So all of this is simply 0. And this is clear. Why it's clear? What is the energy of the lowest state?
0.
It's 0. So I don't really care who sits over there because the energy is 0 and the contribution is 0. Okay. Great. So we have this. Let's write it down. We have u, and we also have the n excited. And excited is G0V divided by K, divided by lambda T to the third power of F 3/2 of the fugacity. Okay. Now, I want to write it in the following form. You see, I have this prefactor G0V divided by lambda T to the third. And I have also this prefactor G0V divided by lambda T to the third. So I want to say that it is simply 3/2 K Boltzmann T. And instead of G0V divided by lambda T to the third, I say, well, from here I know that G0V divided by lambda T to the third equals to n excited divided by F 3/2 of the fugacity. Why I'm doing that? Because I know what this function converges to below the critical temperature. Fugacity, I don't know how it goes, but the polylogarithmic function of fugacity for temperatures lower than T0 is simply F 3/2 of 1. This is why I'm doing this. Okay? What I have over here is n excited average multiplied by F 5/2 of the fugacity divided by F 3/2 of the fugacity. Now, this is a very nice expression. Why it's a nice expression? Because you see, I know how n excited behaves. I have an explicit expression for this guy. Below the critical temperature and above the critical temperature. The only thing that I need to consider is the behavior of the ratio of those two polylogarithmic functions. Okay? That's the only thing. Now, we can look on two limits, the large temperature limit and the small temperature limit. Why I'm looking for the large temperature limit? So when T is larger than TC. Because I can check myself in this limit. What do I expect to observe for the energy when the temperatures are extremely high?
Ideal gas.
Ideal gas. What applies to ideal gas?
3/2 Boltzmann.
Equipartition theorem, right? So for the ideal gas, the energy at very high temperatures is 3/2 K Boltzmann T. This is just the what? The kinetic energy multiplied by the number of particles. What do we have over here? Look on this guy. It's exactly 3/2 K Boltzmann T multiplied by the total number of particles that I have inside my system. And surprise, surprise, when I calculate this guy, I will see that it converges to 1, because what is this? This is F5/2 of e to the power beta mu divided by F3/2 e to the power beta mu. Now we know that mu is smaller than 0. The chemical potential for large enough temperatures it always has to be below 0, but it's below 0. Beta, it's 1/K Boltzmann T. Right? So all of this converges to what? To the behavior of 1. And we observe exactly that U goes as 3/2 K Boltzmann T and excited. Okay? Equipartition theorem. Great. What happens at temperatures which are below TC? Okay? T below TC. Okay? Let's look on this part. So below TC, we know that U equals to 3/2 K Boltzmann T and excited multiplied by T below TC, F5/2, and I just supplement 1 over there, divided by F3/2 of 1. Why it's 1? It's 1 because I don't know what the fugacity looks like. This is true, but I know that the polylogarithmic function converges to the specific quantity when the fugacity goes to 1. Okay? So this is my behavior. Okay. So U equals to 3/2 K Boltzmann T, and I will write it down, the total number of particles, N, multiplied by N excited, divided by N, multiplied by this prefactor of F5/2 1, divided by F3/2 1. N excited, divided by N, we know what it is. It is T divided by C to the power of 3/2. Okay. So what we obtain, U, is 3/2 K Boltzmann T N, the total number of particles that we have inside the system, which is a constant, which satisfies the equipartition theorem. There are no interactions, and there is this condensation that occurs. So basically, in some sense, there is interaction. The interaction is all the particles want to see the lowest possible level. Okay? No kinetic energy whatsoever. So it multiplied by a numerical prefactor, F5/2, F3/2 of 1, which is a constant, multiplied by T divided by TC to the power 3/2. So if I plot this, U as a function of temperature, I will observe the following result. So I have not a linear behavior. Sorry. I have something which grows sublinearly. No, I'm yeah, superlinearly at PC up to CC. And then eventually it converges to a straight line. This straight line is 3/2 K Boltzmann Pn. And I have a peculiar point over there. So if I'm looking on the temperature, well, I can miss it, right? If I'm looking on the temperature, the transition is focused over here. If I'll focus on this point, I will see that there is something goes like this and then goes like that. It's hard to see something like this in an experiment, or almost impossible. If I'll measure just the temperature or as just the energy, I won't probably see anything. Okay? So this is why people measure specific heat. Okay? Because when I'll measure the specific heat, CV equals du to dt. Okay. I'll perform the derivative of this guy. Okay. I perform a derivative of this guy. I will obtain the following result. So this is temperature. This is CV. I know that something peculiar will occur at DC. Okay. And what happens is, well, when you take the derivative, you'll get this part, okay? And this t to the power to DC divided by something. So I'll get a function that rises up. At this point, you see the derivative, something peculiar happens, and this is u. So are going to have a cusp, a chupchik, exactly at DC, and it will decay. Sorry. It will decay to a constant for large temperatures. You know what? I'll make it a little bit more pronounced. We'll have a cusp, a chupchik, at the critical transition. And this is what is observed in experiments. So all this business about Bose-Einstein condensation started from this. Okay. This is called a lambda transition. Why a lambda transition? Because apparently all of this resembles the Greek letter lambda. Anyhow, although this heat capacity is important and the behavior of the energy looks nice, well, something peculiar happens over here. The only critical thing, and this is the physical explanation, is specifically the occupation number. You cannot see, you don't see it experimentally, but this is the whole physics, which tells you that for high enough temperatures, this fraction is exactly 0. Below specific temperature, it rises up and it goes to 1. Okay. So it's in some sense counterintuitive, right? You have infinite number of states and still one specific state somehow not affects, but it attracts majority of the huge number of particles. It's not that, well, there are 100 particles, 200 particles. It's a macroscopical number of particles that sit exactly at one specific microscopical level. Okay? This is what gives rise to very interesting physical phenomena. So this condensate phase, this is how it's called, This is what gives rise to very interesting physics. So anytime that you see something like that, usually the behavior of the system is going to be counterintuitive. What do I mean by counterintuitive? So usually, this is how our perspective works, is when we look on physical behavior around us, we assume, unless it's one single particle in a box or connected to a spring, which boring and simple, and this is what we study in mechanics. But when we look on the outside world, it is accumulation of many events. Okay, so if you think about the following thing, if we have a wire inside and we put an electron inside this wire, okay, and we apply an electric field, okay, apply electric field actually in the other direction. What will happen to those electrons is that we'll try and go to the right-hand side. Okay. In between, well, there are some obstacles inside the wire. There are atoms, etc., etc., etc. So our electrons will try to wiggle their way around this guy, okay, those guys, and this is how current is occurred. Now, due to interactions between those electrons, okay, and the other particles inside the system, okay, what happens is that they lose energy. Okay? They lose energy. The moment that they lose energy, this is what we call friction, or in electrodynamics, we call it resistivity. Resistivity is due to a lot of interactions, impact of everything that we have inside. Friction is heating up, the energy is lost completely. Okay, so this is the behavior that is determined by many interactions with many obstacles. Okay, think about that. So, and this is our intuition. You have not one event that determines everything, but many, many interactions, many, many events. Great. Now, what will happen is, if I'll tell you that, no, the behavior is determined by one single event, not many interactions, but one single event. Either it happens or it's not happens. So what will follow is that I can cancel resistivity. I can cancel the impact of everybody else. Because if I'm looking only on one specific event that determines everything, okay, or one specific electron or one specific level that determines everything, the behavior is going to be completely different. And this is what happens in the condensate phase. Instead of having an accumulation like for fermions of many events, it's one specific state that determines everything, and I can lose the friction effects. It happens for electricity, it happens for fluids, there is superfluidity, and I have all different kinds of other aspects that are determined completely counterintuitive. The moment that I have this one big fellow, one big state that attracts everybody, the behavior is going to be completely different. So this is the point when I stop describing Bose-Einstein and Einstein condensation. I think we'll take a break for 20 minutes. And after 20 minutes, we'll start Ising model and modern phase transitions, right? Thanks. Yes, okay.
אבל כל החשוב שלנו עכשיו להתבסס על זה של המצב הכי פחות אנרגטי הוא אפס.
כן.
זה לא אומר שהאלקטרונים במישור הזה לא יעזבו בכלל, אז כאילו מה נוצר?
ברמה עקרונית, אתה תמיד יכול להגיד, רגע, זה לא אפס, זה איזשהו אפסילון מאוד 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 קטן. המאוד מאוד מאוד קטן הוא 10 במינוס 20 ומשהו, ושם. זאת אומרת, אתה תחשב את זה, זה 10 במינוס ומשהו. זה פחות או יותר, כן, אתה מקפיא אותם ומשהו אחר. כן.
אז סבבה, אז יזוזו מאוד לאט, אבל הם לא יזוזו, אז כאילו מה זה...
לא, הם הולכים יחד. קורה זה כשכל הדבר הזה מתחיל לזה, משהו אחר. בנוסף, אני מפעיל שדה חיצוני. פה זה קופסה סגורה. אני מפעיל שדה חיצוני, והם מגיבים לשדה החיצוני הזה.
אז זה לא אומר כאילו שיש להם אנרגיה ואז כל הדבר הזה כאילו...
אבל זה אנרגיה של כולם ביחד. אם אני מוסיף, זה כמו שאלות של עוד. אם אני מוסיף קבוע, הקבוע הזה יכול לעלות אותי למעלה. הם כאילו יושבו ברמה של הדבר הזה הקבוע הזה שהוספנו, אוקיי? לא יהיו לי אקסיטציות כלפי מעלה שבעקבותיהם אני יכול לאבד אנרגיה, והם כולם זזים באנרגיה הקבועה הזאת שהוספתי. מה זה האנרגיה הקבועה? זה הכוח החשמלי שהפעלת, והם לא מאבדים שום דבר. זה בדיוק, זה נקודה מאוד טובה. אם אני לא אפעיל כלום, אז ישבו למטה, אני אפעיל משהו, פה איפשהו שהפעלתי. הפעלתי שדה, כולם מתחילים איכשהו לזוז.
למה מותר לך להשתמש בכל הדברים שעשינו אם יש שדה? זה מחוץ לשיווי משקל.
מה? זה כבר שאלה, איזה שדה? אז אתה צודק לגמרי, אבל יש משהו שנקרא linear response. ההנחה היא שכשאני מפעיל שדה לא גדול מדי, הוא לא שובר, אני נמצא קרוב מספיק לשיווי משקל, ואני אשתמש בפיזיקה של שיווי משקל, פחות או יותר. עכשיו, בעל מוליכות לדוגמה, אני מפעיל שדה חזק מדי, הדברים האלה יתחילו לשבר. זה יכול להיות שדה מגנטי חזק מדי, זה יכול להיות שדה חשמלי חזק מדי, וישבור את העל מוליכות. כן, צודק. עכשיו, השאלה האחרת שתמיד נשאלת פה, נניח אני רואה על מוליכות. עכשיו, אתה לוקח את התיאוריה הפשוטה, היא לא פשוטה, BCS, זה תואר שני, של דברים נקיים, אתה אומר, אם יש לי שיווי משקל, אני לא רחוק משיווי משקל, איפה זה אמור לעבוד? ניתן לך טמפרטורות של על מוליכים שהן מאוד מאוד נמוכות, סליחה. אנחנו יודעים שבפועל כרגע יש טמפרטורות יחסית גבוהות, זה מינוס 100 מעלות נניח, אבל יחסית גבוהות, שבהם עדיין יש לך על מוליכות. שאלת השאלה, האם זה בגלל ששברתי איזשהו שיווי משקל, האם לא הכנסתי עוד כל מיני דברים פנימה? זה שאלות קריטיות שאנחנו לא יודעים לתאר אותן. כן.
וגם עוד שאלה על מוליכות, בסוף...
אתה צריך לשאול את יונתן. אבל בסדר, אין בעיה, כן.
בסוף, כאילו יש לי פרמיונים שעושים פארינג לקופר פאר שהופכים לבוזונים.
כן.
הטמפרטורה שבה הם עושים פארינג והטמפרטורה שבה הם מתאבים, זו אותה טמפרטורה בהכרח או לא?
זה מאוד קרוב, כן. הפארינג יכול להתרחש כבר, לא, אבל הפארינג יכול להתרחש כבר לפני זה. אתה תסתכל.
כן, אחרי הוא בוודאות לא יכול להתרחש.
בדיוק. כלומר, אתה צריך, שכל הטמפרטורות הקריטיות שאנחנו מדברים עליהן, אתה צריך שזה יופעל על בוזונים. אם החלקיקים שלך הם לא בוזונים, לא יקרה לך כלום, כאילו, הם לא יזוזו.
אבל הם יכולים להפוך לבוזונים גם לפני שהם מתאבים.
רמה עקרונית כן. זה כבר, אתה מבין? אבל פה נכנסות השאלות, מה גורם להם להפוך לבוזונים? איזושהי אינטראקציות עם החומר, שגם שם הטמפרטורה איכשהו נכנסת פנימה. אז ההשפעה לא רק בסדר על הבוזונים, אלא גם ההשפעה היא מה קורה לאלקטרונים שהופכים להיות כאלה וכאלה וכאלה. בהיליום 4 זה אחרת. כאילו, כי הוא כבר בוזון. כבר בוזון.
אבל אני יכול לקחת נגיד גם הליום 3.
הוא לא יהיה בוזון.
הוא לא יעשה קופר.
הוא לא יעשה.
מה ההבדל?
הוא לא בוזון, קוונטי.
לא, אבל גם אלקטרון הוא לא בוזון, לא יהיה קופר.
אבל לא, בוא נגיד ככה, אני לא מכיר תופעות שהם הצליחו לעשות בו איינשטיין קונדנסייט מכל מיני דברים כאלה. אתה ברמה עקרונית, כן, הרעיון של קופר הוא נכון. נניח אפילו אם תיקח פרמיונים, תחבר אותם איכשהו, אתה תקבל בוזונים, ואז הכל זה עובד. זה עובד עבור אלקטרונים. האם אתה תצליח לעשות את זה מאטומים אחרים? ברמה עקרונית זה אפשרי, אני לא זוכר מתי ואיך עשו את זה.
אוקיי.
אבל רוצים לדוגמה בוזה קונדנסייט עם פוטונים. כי הם כבר בוזונים. כי הם בוזונים, ואפשר לעשות את זה. כן.
ולגבי הקבוע, איך תלוי בטמפרטורה?
זו שאלה, אבל הוא לא, ברמה עקרונית הוא יכול, אתה צודק. אבל הוא לא משפיע יותר מדי, כי בסוף כל הגזירות האלה, כן, זה מוסיף לך איזשהו ערך קבוע שם. זה כל מה שזה יכול להכניס לך. וזה לא כל כך אכפת לך מהערכים הקבועים. גם נניח שהוא כן, הוא בסך הכניס עוד ערך קבוע.
קבוע ב-TC.
בדיוק.
קבל איזשהו ערך.
כן, בדיוק.
אוקיי.
עכשיו TC הוא תמיד נורא ספציפי, אז זה לא כזה משנה. נשאיר את זה פה.
כן, אני עכשיו מורה חייבת. מאוד רציתי שהיא טכנית לא חייבת, כי אף אחד לא מבין תתפוס אותה, אבל היא מתעקשת על כל הזמן. אוקיי, ללמד על זה.
זה חלק מזה.
זה, כן. התרגשות של... כן. עכשיו זה... אבל היא מלמדת כיתה ט', אתה יודע, זה הכל.
אני גם לא רוצה למכתה יום.
לא באמת. בכיתה ט' מסתבר יש גם, היא מלמדת אשכרה אנרגיות למיניהן, אנרגיות חום, אנרגיות...
אז מה לשנת מלמד? אז רק את השכבה שלנו, זה היה שנה או שנתיים שבנט היה שר לחינוך.
כן, וואו, היה כל כך הרבה שנים. לא, את האמת, 2001 לפחות אחד, כי אני זוכר כל פעם שאני סיימתי שנה, שמעתי ששנה הבאה לכיתות שהייתי, התחיל קצת את החופש פה ופה ודברים כאלה, ואני יצאתי מיסודי, קיצרו ליסודי את החופשים, יצאתי מזה.
אני כל מקום שעזבתי עם לקח הלכתי כמוננו ויש קבוע אחרי
מבחינת מגמות, בתיכון שאני כן עשיתי פיזיקה בכיתה ט', אבל מגמת פיזיקה, לא עשיתי את זה, סתם למדתי פיזיקה וכימיה, ואז בכיתה ט', ממש מבחן ללימודים של חינוך מדעי בתל אביב, שם הולכים לבית ספר קיצור, בגלל למדעים.
כך שנה אצלי בו. היה כזה, כן, היה כזה כאילו.
לי היה בן עד הבית, כבר שאתה יודע לחתורה, בגלל כיסוי ראש.
נכון, הייתה מישהי אחד אצלנו בשכבה, שאיך שסיימנו את הלימודים היא ישר...
לא, אני יודע לפתור עם כיסוי ראש, היא הייתה נשואה. היא נכנסה להיריון בגלל לא ההפך. בגלל אני נזכר בזה, נזכר פה בזה.
אח שלי הקטן, ויש לו... הוא מייחד לי בינינו שאני ישר בזה. נותן שברה ואורחה.
בגילת הסיפור, בגילה של השחור שלי.
בעבודה שלי
שלושה חודשים צעד את לי.
בעבודה שלי בסגת עליי וקצר אותי, אבל כל עוד זה לא יהיה לי. אני...
תנו בן אדם הזה, אני הייתי
תמיד אפשר להביא לכם אחר כך.
גם לא איתו.
לא, נו.
אני יודע, אבל...
הם ידעו שהם רוצים להתקפן, אז זה לא כאילו מפריע להם. אבל ים.
משלים מאפס, יש לי רק מלבד אני זמן לזה, זה הכל
אני חושבת שיש את מלפיס במועד השני.
בוא נדע למתכנס אבל מועד א' נופל לי יומיים אחרי המבחן, כאילו נראה לי לפקס על המבחן הזה, ואז ככה מועד ב' לא ייפול לי יום.
לא, יש לי יום אחרי יום מבחן ודוברת וכאן.
אני עצוב לי לך, אבל מצד שני, הפינה הזאת תיברך.
אני גם ממש חשבתי עליך כשראיתי את זה. אמרתי וואו, אם זהו מתמודדת עד עכשיו.
שלא מילים, אבל אני רוצה להיות מילים. שבאתי תיכות לחוד.
מה, מעונח, לא בממצא. הלוואי.
לא, בעצם נסתרים זה יותר סבונות, זה יותר בייסטייק.
מאיפה אתה יודע את כל הדברים האלה?
אני כאילו, נסתרים זה בעצם. אני יודע שהאסיד התכוונת למשהו אחר.
לא, כי זה גם לזה קוראים, הקרחונים, זה הפיפר, כי זה קרחון שמתנגדים עליו.
לא שלמה. מה זה? יואב וניחל על השם.
מה שלומך?
אבל
שמחה גדולה.
כן,
אחרי תיאוריה.
סתם קרחון?
אמיתי, כדי להיות ממש לצאת בטוח, כדי להיות לגמרי לצאת בטוח, אני אצליח איזה 2.4 נקודות מתרגיל 4, משהו כזה. זה כדי להיות ממש לצאת בטוח.
יש לך כבר 9 מ-1, לא?
כן, 9.5.
2 כנראה 10, גם אם 9 זה בסדר.
2 זה שלך? לא, כן, שמתי את זה. בשתיים, אני לא בטוח שהוא יקבל אותם. נגיד בשאלה עם העצה הזה, שבו הקוד פונקשן יכול להיות גדול מאחד, שם אני לא יודע אם צדקתי, אין לי אינטואיציה לשאלה הזאת.
זה על...
כן, ולא. אני צריך לקבל ציון ואז אני יודע.
אז בוא נגיד, אני אעשה תרגיל 4, 2.4, משהו פי הקהל.
נכון המקרה שהיה לי,
תמיד מבקש קוד.
שאלתי את ה-ChatGPT,
כן.
הוא אמר שעשו ניסוי בהליום 3, גם זכו בנובל על זה ב-1996.
זה משהו אחר. אבל איך?
הוא רשם דרך קופרטוס.
נכון. זה לא שהוא מתאבד לבד.
כן.
All right. The second part of this lecture today, we're starting a new topic, and we're going to talk about phase transitions and the Ising model. Phase transitions and Ising model. Now, I think it was by the end of the first third of the semester that we discussed the phase transitions and the phenomena, and we discussed it from the perspective of thermodynamics. So something happens to on the thermodynamic level, we break specific stability conditions. There can be a jump in the entropy, there can be a jump in the volume, and this was the perspective, right? Now, what I would try to describe today is more microscopic perspective of what happens there on the microscopic level and how. Now, as almost every topic that we start with description of, okay, so what happens on some physical level? Now, in physics, usually, it's sometimes not true, but in physics, usually, it's the experiments that lead the way. In a lot of cases, theoreticians develop a lot of math, theory, et cetera, but whatever paves the way of physics is new discoveries are usually made in the experimental labs. And this topic of phase transition and Ising model is based on a very nice observation of Pierre Curie, and it's called transition from paramagnetism to ferromagnetism. So paramagnetism, and we have ferromagnetism. So we all know that there are magnets in our world. So basically they apply intrinsic magnetic force on their surroundings, okay? On the other hand, we have different materials that are not magnets, okay? They have absolutely no magnetic momentum, and et cetera. It was discovered that there are some materials, okay, that behave sometimes as magnets and sometimes as paramagnets. So there are materials, when we look on the magnetic moment as a function of temperature, they behave in the following fashion. For high enough temperatures, the magnetic moment is exactly 0, okay? So we take a bunch of this material, some specific metal, and we start to cool it down. We cool it down and we cool it down, so it's somewhere over here, and the magnetic moment is still 0, and it's 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 0, till we reach a specific point, TC, when suddenly, out of nowhere, a magnetic moment appears. So it's not that I am applying an external field, electric field, magnetic field. The only thing that I modified is the critical temperature, okay? And then can appear a positive magnetic moment, and sometimes there can appear a negative magnetic moment. The temperature at which it appears, called TC. Now this TC, we can say critical temperature, but it's had the original name. C stands not for critical, but Curie. And it's not Marie Curie, it's her husband, Pierre Curie, that made this discovery. Okay? So the idea is you take a paramagnet. Okay, what is a paramagnet? Paramagnet is a material that has no self-magnetic momentum. So this is paramagnet. Paramagnet. You cool it down, you do not apply external magnetic field, you do not magnetize it, you do absolutely nothing. You just change the temperature of the material and it becomes ferromagnet. Right? Now, this is a little bit unexpected, right? So I would expect that, well, if there is some sort of magnetism, I should apply it a little bit more magnetism and extend it, increase it. But the only thing that happens over here is that I modify the temperature, and that's it. Now, moreover, an additional experiment that we can look on is the behavior if I'm, so this is a static experiment, right? So I focus on a specific temperature, I keep my material in this temperature for a while, I measure the magnetic moment, and it gives me nothing, 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 nothing. I go over here, maybe at the beginning it will produce nothing, 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 but after a while I can observe a positive magnetic moment or a negative magnetic moment. And it will stay like this for a very, very long time. But an accompanying effect was also observed, which is more of a dynamical effect and not a static effect. And what is this other effect? So if we look on the magnetic moment, but not as a function of temperature, but as a function of external magnetic field, H. Okay? So the regular paramagnet behaves in the following fashion. You start at 0, okay, and you have 0 magnetic moment. You increase your external field a little bit, and your magnetic moment rises up. You extend it a little more, it rises up. You extend it a little more, it rises up, and up it goes. Up, and it converges to some specific quantity, and it can never overcome this specific quantity, okay? Now, so you started over here, and you went up, and you converged to a specific quantity, okay? Now, what happens if you keep this material at a specific external field, and then you start to lower this specific, the external magnetic field, okay? H, the external magnetic field that is applied. So if I'm now decreasing it, the process is totally reversible. What it means? It means that I will go down and down, down, and I will follow exactly the same line as when I was increasing my magnetic field, okay? So I will reach over here, and then when I'll decrease my external magnetic field even further, I will get negative magnetic momentum, and eventually I will converge to the minus M0, okay? Now, so what I've done, I've reached to this point. Now from here on, I also can reverse the process and I will start to increase my magnetic field, my external magnetic field, and I'll go backwards. And I can do this all day long, and the only thing that I will get, I will follow this one specific curve. I will have some fluctuations due to finite temperature, and this is what I will do. This is a paramagnet. You apply external magnetic field, you get some magnetism. You decrease, you get negative magnetism, okay? Nothing bad happens. In ferromagnet, okay, in ferromagnet, well, this is what happens in this region. In this region, something else occurs, okay? What occurs in the ferromagnetic regime? So this is H, this is M, this is ferromagnetism. So you start from zero. Let's assume that you had a zero magnetic field. You will increase it, and at the beginning that it behaves as regular paramagnet. Okay, you reach this point. Now in paramagnet, when you reach this point and you reverse the external field, you go downwards. In ferromagnet, instead of going downwards, you do go downwards a little bit, but you actually do not reach zero. Okay? You reach a specific non-zero self-magnetism, even when your external field is zero. Okay? You will continue now to decrease your external magnetic field. Eventually, the field, external force, will overcome your self-magnetism. Okay? And you will go down, and you will eventually reach some specific negative value. Okay? So we started over here, reach this behavior, we have a saturation, we go back, we expect to go to zero. Instead, we're going, and we still have a positive magnetic field. We have a positive magnetic field even when we had negative external magnetic field. We saturate at some negative value, and when we perform,
you can see the lower order graph.
Thank you. And when we go backwards, we also do not go back to zero, and instead we do something like that. Fine?
Yeah.
Okay. So this is the behavior. So you will have a closed loop, and this loop has a name. It's a hysteresis loop. Okay. And the fascinating thing is that when you go in the paramagnetic regime over here, behave like this. You cool everything down and it starts to behave like this. Right? So now this is a static behavior. Okay? You do not apply external field, not nothing. You just fix a temperature and you wait till the magnetism reaches a specific value. Here you measure, and you basically pump, you increase or you decrease your external field. Okay, so somehow you're able to obtain this ferromagnetic behavior for low enough temperatures, when for high temperatures you have something completely different. Okay. Now, immediately arises the question, how come? Okay. It's not that we applied something for, so it is an intrinsic property of the material that modifies as we change the temperature. It's not that we did something to the molecules. It's not that we modified it and applied some other field that penetrated into the material and caused the damage or whatever. It's just some specific interactions between the molecules of the material. Okay? When the temperature is high enough, they give rise to behavior number A, and when the temperature is low, they give rise to behavior number B. Okay? And there's some sort of a transition. We call it a critical transition between those two behaviors. Now, this gave rise to the microscopical theory of phase transitions in general. Now, when you think about it, what do you expect? So what is magnetism in general at all? So magnetism in general, we can assume the following thing. Say we have some charge carriers, okay? And those charge carriers, if you have a classical picture, the charge carriers, they rotate somehow, okay? And because they rotate, you will have a magnetic field in a specific rotation. They can rotate clockwise or anti-clockwise. This is a simple classical picture of how magnetic field can be produced due to charge carriers. Now, from quantum mechanical perspective, the only thing that matters, you can say, well, I need spin and some Bohr magneton, okay? So I can have a specific spins, okay, and of different particles, and those spins, okay, or the magnetic moment due to the spin is the Bohr magneton multiplied by the spin of the particle, okay? But the direction of all of those spins is absolutely random because these specific rotations can be absolutely random. The directions of the spins are absolutely random. So if I'm looking on a specific material, I will have a bunch of different spins in a completely random directions, okay? And I know that I have to add them up vectorically. I have Z direction, X direction, Y direction, and I have huge numbers of those spins, or I have huge number of some rotating charge carriers. So the zero magnetic, self-magnetic moment, it basically says, look, everything is disordered, okay? If everything is disordered, there is no specific direction that all the different particles point in this direction, okay? And due to this fact, the total magnetic moment is zero. We're summing up a lot of different vectors. The orientation of each vector is completely random. There is no preferred direction for any moment. And voila, we have zero magnetic moment. M equals to zero. Okay, so we put here mu I, mu zero psi. So the magnetic moment, it's a summation. I goes from 1 to n if I have large number of n's of mu I. And because everybody are oriented in completely random directions, you have no magnetic moment. Okay? Now, this is why the majority of the materials around us are not magnetic in a way. They do not have self-magnetic moment. Because in order for a given material to have a specific magnetic moment, we need to have order, meaning all of particles should be organized in exactly the same direction, or the spins should point out in exactly the same directions. Okay. So zero magnetic self-magnetic moment equals to disorder. Non-zero self-magnetic field moment equals to order. So somehow, the transition that we observed, this is T, this is M. What we see is something that goes like this, then can go like this, is a transition between disorder to order. Now, I can understand order if you have preferred direction, okay? What do I mean? So if you remember, I plotted this plot that self-magnetic moment as a function of external field for a paramagnetic material was growing up like this and decreasing like that, okay? This is clear. Why it's clear? It's clear because there is an interaction between the external magnetic field and the self-magnetic moment. The energy is minus mu h. Okay. What it means? It means, oh, I'm sorry, it's not minus mu h. It's mu h. minus. It means that I would like to be directed or in the direction of the external applied field. So if I have an external applied field and, my spin is oriented somehow, if my spin is going to be oriented in the direction of the applied external field, what happens is my energy will get lower, right? You have this minus sign over here. The moment that the energy gets lower, it's a more preferable state, okay? Therefore, I prefer to be aligned with the external field, okay? So this is what happens for paramagnet. I apply external field, I have a preferable direction due to the application of external field, and my magnetic moment grows. When I apply a negative external field, the preferred direction is in the direction of the negative magnetic field, so my self-magnetism becomes negative. Right? So there are no big surprises here, right? I apply external field, this external field creates a preferable states that are aligned with the external magnetic field, and voila, I have magnetism. Great. But here, I do not apply anything, right? I have self-magnetism, but this self-magnetism is not created because somebody from the outside, and this is the idea of external magnetic field. The external magnetic field tells me there is a preferred direction. Who said so? Some guy that applied it. Okay, I have extra universal experience. Somebody from the outside of the system applies, says this is the preferable direction, and everybody follows. Okay. Now here the order self-organizes without anybody telling the spins that, well, you should point over there. Okay. Now this is why there's sometimes positive magnetic self-magnetism, and there are sometimes negative self-magnetism, okay? There is no preferable direction, but what happens is there is a chunk of particles, chunk of spins that are pointing exactly at the same direction without anybody telling them to do so, okay? So this is a spontaneous transition from disorder, where everybody are disoriented, to order when a huge number of particles, big number of particles, are somehow pointing in the same direction and self-magnetism arises. And it's interesting to say how and why. Because as I told you, it's clear if I apply external field. It's absolutely not clear where it's coming from. And the only place that it can come from, because I do not apply external field, are self-interactions between particles. If you remember, I always told you the following thing. This is like a dogma in our class. We somehow need to neglect interactions. We somehow need to describe the system without interactions because, well, technically we cannot write or solve a partition function when there are interactions between particles. And the only thing that we can do eventually is as describe as if everybody are non-interacting. So we have a gaseous description of almost everything that we've done so far was to describe gas. It was a complicated gas, but eventually it always was a gas. Okay? Even for fermions, it was a gas. For boson, it was a gas. There were some peculiarities to this gas, some specific states that maybe attracted the particles. Okay? But eventually, we almost always neglected interactions. Sometimes we haven't neglected them, but we created new effective particles with additional interactions. So basically the interactions cause the particles to be something different, like phonons. Okay? We haven't treated particles as non-interacting. We said, oh, there are groups of particles and the phonons are non-interacting. But this tells us that interactions are super important and interactions cannot be negligible. The specific transition, order to disorder, that appears only due to the interactions between different components of the system is basically saying, well, whatever you have done, there is a flaw. And the flaw is interactions are super important. Whenever you want to describe anything that's related to phase transitions, you have to take into account interactions. They're critical, they're sitting there, and somehow they're going to affect your whole behavior. Okay, now, a lot of words. By the way, this is also called a spontaneous symmetry breaking. Why? Well, if you have a disordered system, everything is symmetric. No preferable direction. So you look over there, you have a bunch of particles pointing in that direction. You look over there, you have a bunch of particles of spins pointing in that direction. Nowhere, no matter where you look, everything looks the same. Okay? You lower the temperature, and like that, the system have a bunch of particles, huge bunch of particles that are all pointing over there. Somehow, symmetry was broken. There is a preferable direction. And it's not that I went there and broke it by hand. Temperature caused it. Now, if you remember, there is always some sort of competition. For very high temperatures, okay, I don't care about the energetic structure, okay, because the particles can be whenever they like, and I look on them as if they are free particles with only kinetic energy. For low enough temperatures, the system would always prefer to sit at the lowest energetic level. Okay, so there is some sort of a competition between this kinetic energy and free motion of particles and the energetic structure. And what this result tells us, the spontaneous breaking tells us that there is a transition from completely free behavior and something which is completely different. By the way, I hope that you noticed that what we've seen for the Bose-Einstein condensation looked exactly the same. So if we look on the N0 divided by N, it also looked like this, right? And if you look on the spontaneous symmetry breaking, magnetization, which is M, temperature.
Scroll down a bit.
Yep. This. So it's very similar. And you can describe it in a very similar terms. Although the transitions are different, but for the Bose-Einstein condensate, the particles could be on any possible energetic level for high enough temperatures. For the lowest temperatures, there is a specific level. It's the ground state of the system where the particles prefer to be. Okay? This is what happens over here. So it's, in some sense, we can say, oh, the system became more ordered. Why it became more ordered? Because there is a preference now to a specific energetic state. The same happens over here. For high enough temperatures, the spins could be in any possible direction. And there's infinite number of different directions, okay? For low enough temperatures, over here, there is a big bunch of those spins. They prefer to be in this direction, this specific direction. So it's different in the sense of here it's we know what the state is the lowest possible energetic state. Here we don't know what's the possible direction that they prefer to point to, but we know that there have to be some specific direction that it's preferable. Okay. In both cases, it happens due to we lower the temperature enough and something occurs. In this case, we started with a bunch of non-interacting particles, and it's the interaction between the energetic state and the particle that creates this transition. On the right-hand side, it's the interaction between the particles and themselves that creates this transition as well. And the first attempt to understand what's going on here and why started in the 20s. We go back to the 1920s, and the first guy who started to try and deal with this theoretically was William Lenz. He gave this problem to his student, which published with Lenz the solution of a one-dimensional system. And the name of this guy was Ernst Ising. The solution of Ernst Ising was wrong. It was later proven by wrong, but the name sticks with Ising. That's what we will describe in a second. The exact solution was postponed until 1944 to the guy Lars von Sacker. This is one of the crucial models of statistical physics of the 20th century. This is the basis how we understand phase transitions today, and it gave rise to a big number of scientific progresses in understanding how statistical mechanics actually works. I will describe to you the Ising model in a second. Maybe we'll start with this tomorrow, not tomorrow, next week. The only thing that I want to say is, you see, there is a problem. And the problem is, in statistical physics, is that we know the fundamental quantity that we need to compute in order to solve everything. And this everything, this quantity, fundamental quantity, is the partition function. It can be a canonical representation or a grand canonical representation. It doesn't matter. It is always the sum of this possible state of the system, e to the power minus beta En. Okay? The energies of the system. Now, what is this minus beta En? So you can say, look, it is, if we want to look in quantum mechanics, we have, instead of writing e to the minus beta En, we can write it as the bracket of e to the power minus beta, the Hamiltonian of the system. Okay? So Z is a sum over N of N e to the minus beta Hamiltonian N, or you have e to the power minus beta Hamiltonian, and you have a matrix, or you have an operator. So the partition function is simply a trace of this operator. Okay. Now, you studied quantum mechanics, right? And in quantum mechanics that you studied, you solved the problem of one particle, maybe two particles, right? The hydrogen atom, and that's it. 3 particles, 4 particles, we already lost. This operator, it's an infinite matrix, and etc. It's very, very, very complicated. Now, so the attempt to describe what happens, even for the magnetic system, when you know that it involves spins, and you know that there are quantum effects that have to be present because those are spins, and etc., etc., etc. So you need to find the Hamiltonian, and you need to find the trace of this huge matrix, and it's impossible. Right? It's basically impossible to do for any real life system. So what do physicists do? What is statistical mechanics is about? And this is all what we've done through this semester, is to say, let's start from a simple model. Okay? What is this simple model? We do not want to include everything into account. We do not want to solve all the Hamiltonian of this complicated system. We want to solve something that mimics whatever happens in true material, and we hope that the physical ingredients that we put inside the system are not too far away from whatever comes from this partition functions over here. Okay, so this is what William Lenz did and got the name Ising. And the idea is as follows. We can look on one-dimensional system. So this is the Ising model. And this idea of reality, of a magnetism, is very simple. So if we look on one dimension, for example, X. So, and we have a lattice. This lattice, it describes the structure of the system. And those blue balls or blue points are particles that can have either spin up or spin down. Okay. And the whole system, the only thing that you look on is those spins. At any point, I, okay, there is a spin that is associated with this specific point. And the spin can have two values, can be either +1 or -1. Okay. So the energy of the system, and in addition, you can also apply an external field, H. Okay. So the energy of the system goes as follows. So first of all, if you look, let's look on the energy I of a specific particle. It has this component of interaction with the external field. So it's H mu, which is the Bohr magneton, multiplied by SI. So each and single particle inside my system has this self energy, which depends only on the external field. Now, we'll see that it actually gives nothing in a sense of phase transitions. So the spins, they have to talk with each other, right? So there are some, you know, from the spins can interact with each other, okay? So we also need interaction term. Okay, and what is this interaction term? So we assume the following. So if we take a spin Si, and we take another spin at position J, Sj. So Si can have values 1 or -1, and Sj can also have values of -1 or 1. Okay, now, we want the following thing. So first of all, because those are unitless numbers, we need to introduce a coupling constant, which is a coupling constant. So we want to take two spins, multiply their values, okay? And this will be proportional to the interaction energy of those two spins. So we have Si, we multiply it by Sj, and here we'll have some prefactor that will depend on the distance between Si and Sj. Okay? So if they are really, really, really far away, they should not interact at all. If they're close, well, the interaction should be good or sufficiently strong. So here we have Ri minus Rj. Okay? And this is a coupling constant. Coefficient, it's not a constant. Now, the only question is how we define the sign. Should we put here a plus or should we put here a minus? Okay, so this we learn from the perspective of experiment. What we expect that at some low enough temperatures, the particles, because we know that for low enough temperatures, there is a self-oriented magnetism. It means that enough of particles are pointing at the same direction. This means that this preferable energetic state should occur when spins are aligned. So if Si is exactly in the same direction as Sj, okay? So this, it doesn't matter if Si is 1 or -1, and Sj is 1 or -1, as long as they have exactly the same value, +1 or -1, this gives us a plus. If they have opposite direction, this gives us -1. Now, we want them to be aligned. Therefore, the contribution of the interaction should be negative, okay? We already know that the system prefers always to go into the lowest energy, okay? So this is what we pick. We erase the plus and we take the minus, okay? So in total, what is the total energy of the system? E. The total energy of the system is the energy due to interaction with external field, but of all the spins. So it is minus, I goes from 1 to n, h mu si. We can do it like this if you want. This is the interactions with the external field. And there is a self-interaction, which is minus. And I have to sum over all the possible interactions. So all the possible i's and all the possible j's. So I do it as follows. I goes from 1 to n. J goes from 1 to n. In order not to count everything twice, I will put 1/2 over here. Okay. And here I have J of Ri minus Rj, Si, Sj. So this is the idea of William Lenz. This is what we call Ising model. I described to you in 1D, but it doesn't matter. You put any lattice in 1D and 2D and 3D, okay? And then you ask the following question. I compute the partition function, which is just a summation of E or e to the power minus beta En n. You sum over all the different states, and you compute the average self-magnetic moment, which is simply mu, a sum, I goes from 1 to n. N is the number of particles of Si. Okay? And how this magnetic moment behaves as a function of temperature. So for 20 years, people only knew how to solve approximately the one-dimensional case. It was a genius work of Lars von Sager in 1944, who managed to solve the two-dimensional case. Nobody knows how up today to solve the three-dimensional case. Nobody knows how to solve two-dimensional case with external field, but the search for understanding what happens in the world and how it behaves, that's what gave rise to the whole theory of phase transitions, renormalization group, and the theory of equilibrium and non-equilibrium statistical physics. What we will see is, we will show, not today, how to solve this model in 1D, 2D, and 3D without interactions, so just for gas, as usual. Then we will develop a theory that's called a mean field theory, that is approximate solution when you have interactions. And we will see that, well, yes, there is a phase transition, even for this simple model. We'll have observer order disorder transitions, and hopefully we will understand something about the role of interactions. Okay, so that's it for today. Thank you.
סטאס,
כן, אני אשלח.
ה-J הזה לא מעניין אותנו, כאילו זה J, כן מעניין הפונקציה, אבל זה לא...
אנחנו נתייחס אליו כאל קבוע, כן, הוא לא כזה מעניין. אבל זה דווקא לא כל כך חשוב. מתברר שהרי הוא תלוי ב-RI-RJ. כשהדבר הזה דועך יותר מדי לאט, ויש לך עדיין אינטראקציות חזקות ממש ממש רחוק, הוא כן משנה את ההתנהגות. אנחנו לא נתייחס לזה, מבחינתנו יהיה איזשהו גודל קבוע. כן. אני אעלה את הכל למודל. אני לא יודע כמה זה ברור, הקשקושים שלי, אבל אני אעלה אותו. לא, 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 ממש לא. כן, כן, זה דברים שונים. זה דברים שונים, בבקשה. כי הפיזיקה קצת שונה. כי בקורי זה אינטראקציה בין הדברים שמרכיבים לך את זה, ובבוזה איינשטיין זה אינטראקציה בין המסבוזונים, זה השליטה של האנרגיית גראונד סטייט. אז זה דברים שונים. ההתנהגות בסוף היא דומה, אבל זה קלאס אחר של בעיות.
זה רעיון של תיאוריה. אני הכנתי חומר, אני אמר...
כאילו, ניקח נגיד שתי ספינים.
רגע, תן לי לעצור את זה. סטופ ריקורדינג.